let's talk about product metrics. So basically, a product space is when you have two metric spaces and you form the Cartesian product of the two metric spaces. Now, there are at least three different ways to naturally define the cross product of two metric spaces. So you start off with the sets, right? So suppose you have two sets A and B, and A is a metric space and B is suppose you have two sets A and B, then A cross B is just a set of um, coordinates, if you will, where the first coordinate is an element of A, and your second coordinate is an element of B. Okay, so the collection of all of those coordinates is A cross B. Now, if we start off with two metric spaces, M and N, then three ways that we can metrize the cross product M cross N are given by the Euclidean metric, the max, and the sum. So we've seen these before because we went over these three examples when we were dealing with R cross R, with R2, okay? So let's just walk through this quickly. Suppose P is a point in M, and I'm just going to say P looks like X, comma, Y. And, suppose P and P prime belong to M cross N. Okay, so P is X comma Y, X is an M, Y belongs to N, and P prime, let's write it as X prime comma Y prime. So X prime is an element of M, and Y prime is an element of N. The Euclidean distance would be to take the distance between X and X prime in M and square it, add it to the square of the distance between Y and Y prime in N, and then take the square root of all of that. For our max metric, we're just going to take the maximum, which is bigger, the distance in the X coordinate or the distance in the Y coordinate, right? And then the sum, of course, is we're just going to add up those distances. So these are all metrics on the cross product M cross N. We have a theorem that gives us a relationship between these three metrics. It turns out that these three metrics result in equivalent topologies. So what we mean is the open sets that you get from using this metric are the same as the open sets that you get using this metric, and they're the same as the open sets you get using this metric. So even though you have different functions for your metrics, the resulting collection of open sets is the same. Okay, so let's actually prove this. We're going to prove this string of inequalities by first showing that the max metric is less than or equal to the Euclidean metric, okay, and so forth and so on. So now, why is the max metric less than or equal to the Euclidean metric? Well, let's look. So I've written the max metric here, and I've written the Euclidean metric here. So is it the case that the max is less than or equal to the square root of this squared plus this squared? Well, think about what would happen if we were to square both sides. So if we had the max squared, is that less than or equal to the first coordinate squared plus the distance in the second coordinate squared? And the answer is obviously yes, because the max is either going to be this or this, right? And so if we square the max, we're either going to get one of this one or we'll get that one, right? And since the distance squared is a non-negative number, this is going to be less than or equal to the sum of both of these because it's going to be one of these, okay? Now, Is the Euclidean metric less than or equal to the sum metric? Well, let's look at this. So I've written the Euclidean metric here, right? I just copied it. And is it less than or equal to the sum metric? Meaning, is the distance between 2 points with respect to the Euclidean metric less than or equal to the distance between 2 points if we just take the sum, right? Again, square both sides to see why this would be true. And when we square both sides, it's easy to see that this right-hand side is going to have this plus 2 times the metric, the max. So the metric in M times the metric, the distance, with respect to the metric for N. Again, since metrics give non-negative values, this term is going to be greater than or equal to 0. So this has to be bigger than or equal to just this. Right? So then if we take the square root of both sides of our inequality, we'll get what we want. Okay? Now, one last inequality. Is it true that the sum metric is less than or equal to twice the max metric? So I've written down the sum, and that's just d sub m plus d sub n. And I want to know, is it less than or equal to twice the max? Well, the answer is yes, because the max is either dm or dn. So twice that is either going to be dm plus dm or dn plus dn, right? And if I compare this to this, if I'm using d sub m as my max, that means that this d sub m is bigger than this d sub n. So I will have greater than or equal to. And similar reasoning shows what happens if the max is the distance in the y-coordinate or the n-coordinate. Okay? So putting it all together, what have we shown? We've shown that this metric, the max metric, gives a distance that's less than or equal to the Euclidean, which will give a distance that's less than or equal to the sum, which will give a distance that is less than or equal to twice the max. Why is this important? Well, because it allows us to prove that convergence with respect to any of these metrics is the same. So if you have a sequence and the sequence converges in the max metric, that sequence is also going to converge in the Euclidean metric. The sequence will also converge in the sum metric. And the last little, and this is a typo, so it should say P sub, oh no, yeah, I just need this. P sub, the last little bullet point here notices that the only way your sequence converges in your product space is if each component converges in each space, okay, in each component of the product space. So why is this true? Why does this theorem hold? And the answer follows from this fact right here. In general, in a metric space, a sequence converges to a point if and only if the distance between the sequence and the point converges to 0. Okay? So suppose you have a sequence that's converging with respect to the max metric. That means that those distances are going to 0. But if those distances are going to 0, then 2 times those distances are also going to 0. Apply the squeeze theorem, and we get that our sum metric goes to 0 and our Euclidean metric goes to 0. So if our P sub n is converging to P with respect to the max metric, It also has to go to 0 with respect to the sum in the Euclidean metric. Okay? And now what if it's converging to 0 with respect to the Euclidean metric? Well, that means this is going to 0. But remember, the max metric is always greater than or equal to 0. So again, we can apply squeeze to conclude that our sequence has to converge, that our distance has to converge to 0 in the max metric. And now once we know that this is going to 0, 2 times it is also going to 0. And now we have this is going to 0, this is going to 0. So we're going to 0 in our sum metric. And I won't go through all the different cases, but you can see that convergence in one of these implies convergence in all of them. Okay? And lastly, to show this, right, our sequence converges in M1 and it converges in M2. Well, we can look at the fact that we can add on that this is going to be greater than or equal to the distance in with respect to n of the y prime, and it's greater than or equal to the distance in the m metric, right? So the idea is that the distance for any of the components is going to be less than or equal to the distance when we are looking at the product spaces. So we can use that same squeeze theorem to conclude that convergent sequences will have their distance go to 0 for each of the component sequences. Okay, the last thing I want to talk about here is how continuity plays with product spaces. So the setup is that we have 2 continuous functions. We've got 4 metric spaces, and we look at the cross product, if you will, of our functions, of our continuous functions. We're saying that if you start off with 2 continuous functions, then the cross product is again going to be a continuous function. And so let me show you what this looks like. The setup is f goes from m to n, g goes from x to y, and we can form the cross product f cross g, and it goes from m cross x to n cross y. And here's how it's defined. So for a point in m cross x, the first coordinate belongs to m, the second coordinate belongs to x. So for your output, the first coordinate is going to be f applied to the first coordinate of your input. And similarly, the output in the second coordinate is going to be g applied to the input, the second coordinate of the input. So our claim is that if f and g are continuous, then f cross g is continuous, right, on the cross product. And let's look and see what that looks like when we want to get an idea of it. So f takes points in m and sends them to points in n. G takes points in x and sends them to points in y. And then f cross the g takes points in m cross x and sends them to points in n cross y. Okay, so we want to show that our f cross g is continuous. So let's suppose we have a sequence. There we go, f cross g is continuous. So let's fix a point p comma q in m cross x. So here's p comma q. So that means here's p and over here's q. Suppose we have a sequence converging to p comma q. So say pn qn converges to pq in m cross x. We want to show that f cross g of pn comma qn converges to F cross G of P comma Q. And this action is happening in N cross Y. That's our goal, because what does it mean to be continuous? We're using our sequential continuity definition. Okay, so we've got our P sub N, so let's say this is P sub 1, Q sub 1, P sub 2, Q sub 2, right? Notice that from our last theorem, this means that P sub N has to converge to P and Q sub N has to converge to Q, right? Because the only way you're having convergence in a product space is if each component converges. This is where we start to smile, because F is a continuous map from M to N. P sub 1, P sub 2, project this sequence onto the first coordinate, onto M, and you're going to get a sequence of points converging to P. F is continuous, so it preserves convergence. So that means F of P sub N converges to F of P over here in our metric space N. And similarly, G of Q sub N is going to converge to G of Q over NY. And now, the fact that both of these converge will force F of Pn, G of Qn to converge to F of P, G of Q in N cross Y. Because again, we're in this product space, and in our product space, convergence happens if and only if each of the components are convergent. Okay, so that's basically the sketch here. So for the proof, you're essentially just projecting each of those, right? Projecting the sequence in the product space onto the component metric spaces. So project it down, or you can project those points over, right? And then use the fact that you've got a continuous map from X to Y to get, to get your convergence over in Y. Okay, one last topic here. Is this business about product space? So this. So we've done this theory for the cross product of two metric spaces, right? And it turns out we can extend this to any finite product very easily, right? So all we have to do is go back to our metrics. Remember these metrics that we gave, right? Euclidean, max, and sum, and we can extend them. So you can imagine, right? So if we had, for instance, not just x and y, but suppose we had x, y, and z, and x, y prime, and z prime, then we would just extend this, right? So it'd be mn and maybe cross O. And you kind of get the idea, right? So the max, not of dm and dn, but dm, dn, and we would add in there do, right? So you can do this as much as you need to finitely, for finitely many for finitely many metric spaces. I will tell you this, it is possible to have a metric space that is the cross product of infinitely many metric spaces, but that gets to be a little more complicated, okay? So for now, for this course, we're just focusing on finite cross products, okay? And then you'd be able to do similar estimates here. I think this factor of 2 would probably change. It might be something where, this 2 changes to the number of metric spaces that you are taking the cross product of, right? But some finite factor, okay? And then we would have equivalence still. The proofs would be the same or very, very similar. And then we would have convergence of the sequence in your product space if and only if each component converges, right? So we would add P3N, and however many you have, okay? All right, so yeah, here we go. For example, convergence in Rm. So here, each metric space that we're considering is the same. It's just a copy of R with Euclidean metric. And we've just written up here that a vector, a sequence of vectors, converges in Rm if and only if each of the component sequences converges, right? And the limit of the vector is the vector where each component is the limit of the components, okay? So that is that for product spaces. In our last video, we'll discuss completeness.